A carbon atom will have 4 bonds when it does not have a formal charge. However, in some cases, carbon may have a positive or a negative charge. When it has a positive charge, also known as a carbocation, it will have a total of 3 bonds. Carbocations are fairly common when we're looking at multi-step synthesis, and carbon loses an electron as part of one of those many-step processes. Carbanions also exist. They carry a negative charge, and they will also have 3 bonds and also a lone pair, no empty orbitals. Let's talk a little bit about resonance. Resonance is the consequence of the way we draw structures. Sometimes when we attempt to draw certain scenarios, certain molecules, single drawing does not adequately describe a chemical species. We can see here, for instance, in this system, the oxygen, both oxygens actually have a negative charge. That charge is actually dispersed throughout that system between those two oxygen atoms, yet there's no way for us to sort of do that partial charge distribution. So instead what we do is that we draw all possible structures and do these double arrows, double-headed arrow, to depict a resonance structure. So what we're saying here is that these are possibilities, and the actual experimentally determined structure is a hybrid between these two. That's what it means to have a resonance structure. Throughout organic chemistry, we will be using curved arrows to show electron movement. This is super important because from my experience, this is one of the most common mistakes. When you're drawing arrows, you're drawing how electrons move, not atoms. Uh, the base or the tail of the arrow will tell you where the electrons are originally located, and then the head of that arrow, the tip, is telling you where that electron is going to go. The sooner you master this skill, the easier the course will be. You will see these arrows throughout the entirety of the course, and in organic too, if you're taking that course, you'll also see a lot of arrow moving. The arrow starts where the electrons are currently located. The arrow ends where the electrons end up after the electron movement. There are specific rules for using curved arrows to describe electron delocalization, in other words, resonance. Never show a single bond or a sigma bond as being delocalized. We can't do that because, for instance here, this is just one pair of electrons. If I tell you that they're moving, I am essentially breaking this bond, unless that is exactly what I intended to do, such as in a chemical reaction where the bond breaks, then it's not really correct. For resonance structures, we're not really breaking any type of chemical bond, so that wouldn't be accurate at all. Second bonds break in a chemical reaction, not in resonance, as I mentioned. Resonance happens for electrons existing in overlapping p orbitals, pi bonds, and lone pairs, not in sigma bonds. Rule number 2. Never exceed an octet for a second row element, carbon, nitrogen, oxygen, and fluorine. The valence shell of an atom in the second row has only 4 orbitals, holding a maximum of 8 electrons. There's no space for more electrons than those 8, so we can't justify adding more electrons there. It's just not a physical reality. Here, for instance, I'm trying to depict in this example these 2 electrons moving towards this bond that would have as a consequence a double bond, but that also means that carbon will form 5 bonds. That does not happen in nature. That would be an incorrect description. That's what we call a bad arrow. Same here and here as well. So we have to keep all of these rules that we learn in general chemistry and we reviewed in chapter 1. We still have to keep them going throughout the entirety of the course. Second row elements will sometimes have less than an octet. That is perfectly okay. That actually does happen fairly commonly, but no more than an octet. Right? We can't hold more. We can certainly have less in some scenarios. Here, for instance, you have a negative charge, and even though you do have a negative charge, the octet rule is never broken. You don't have an excess of electrons. You do have fewer than 8. You actually have 6 here, and that's okay. What that means is that the system is unstable and it'll likely undergo some chemical process later on. Let's talk a little bit about formal charges when we talk about resonance structures. When using curved arrows to derive resonance structures, you will often have one or more formal charges to contend with. As you know, molecules like to be in a neutral configuration, neutral charges if possible, Although in some cases you will have a charge separation, a plus and a minus. There's a few things to consider whenever you are in those specific scenarios. Let's look at this structure first. Consider the resonance structure derived from the curved arrows. You can see this lone pair is moving towards this carbon-oxygen bond. It'll generate a double bond. And then this double bond, you have two electrons moving towards this carbon atom. So you will have a lone pair of electrons here and a single bond here as a consequence, such as the one that we see here in this first drawing. We can draw the other resonance structure by following the instructions provided by the curved arrows. So just follow the arrows, look at where the electrons land, and that's pretty much it. There's nothing else associated with this type of exercise. However, once we've done the arrow moving, we located the electrons, we placed them, we have to also include information regarding the charges associated with the molecule. Now, oxygen lost 2 electrons, so it will acquire a plus formal charge, and this carbon atom acquired electrons, so it will have a negative formal charge. Now, when we start working on these exercises, which I recommend that you do, practice as much as you can, you're gonna see a lot of patterns emerge. These are some of the more common ones, 5 general bonding patterns in which resonance happens very often. The sooner you recognize these patterns, the easier the rest of the chapter becomes. Some of these scenarios include an allylic lone pair, an allylic carbocation, a lone pair adjacent to a carbocation, that plus side in the carbocation, a pi bond between two atoms of different electronegativity, conjugated pi bonds in a ring. And as you can imagine, the only way, or the best way really, to recognize these patterns is to practice as much as possible. This is a course where practice is actually very, very important. Let's look at some of these patterns. For pattern number 1, the allylic lone pair, vinyl and allyl refer to atoms of the pi bond next door to the carbon-carbon double bond, respectively. This is a vinylic position. You can see the carbon, that double bond, and then adjacent, or right next to those carbon double bond, you have the allylic positions. So double bond right next to it, this would be allylic, right bond, right double bond right next to it, nothing, next neighbor, that is not an allylic position. It's important that we sort of understand this difference, because resonance depends on whether you're in the allylic position or not. So I would expect resonance between these in this area, but not in this area, definitely. We look for allylic lone pairs because they will be resonance delocalized. All the lone pairs drawn in this example are allylic. Double bond, neighbor, double bond, the neighbor, double bond, neighbor, and so on. You get the idea. That's one of the patterns that we are looking to recognize. For that, we actually need to draw 2 curved arrows to show the delocalization of the allylic lone pair. So if you look at this structure right here, we need to show an arrow for the electrons here and the electrons here, what's going to happen to each of them. So you can see the lone pair moves, and then the double pair also moves. If we only do one of the arrows, then you will inevitably end up with likely carbon with 5 bonds, which is not something that exists in nature, right? It's one of the big no-nos in organic chemistry. Same thing happens with all of the other scenarios. 2 arrows, right? From lone pair to carbon single bond, from double bond to the other side of the carbon-carbon double bond. When the atom with the allylic lone pair has a negative charge, the charge is delocalized with the lone pair, as we can see here. You can see the lone pair sort of migrated, and generated these 2 structures. The same with pretty much everyone in this set of examples. If the allylic atom is neutral, then it'll become positive, and the atom receiving the lone pair will become negative. Let's look at that second pattern, allylic carbocations. Only one curved arrow is needed to show resonance in this scenario. So here, for instance, this will be my allylic carbocation. So my double bond, and then adjacent to it, I have that positive charge. So what will happen is that the second pair here in the double bond will migrate here, right? And it will neutralize them, and then the positive charge sort of migrates to this side. If there are multiple double bonds, such as in conjugated systems, then multiple contributors are most definitely possible. They are drawn by moving one electron pair at a time, sort of what we see here. So we have the double pair, double bond, goes here, and then the positive charge sort of migrates in the opposite direction, and so on. And you'll do that as many times as you can in highly conjugated system. In this case, the consequence is that the hybrid is made up of 3 resonance structures, as shown in this little scheme here. Let's look at the third pattern, lone pair adjacent to a carbocation. Now when that happens, you only need to use one arrow that will tell you where the lone pair is moving. So you go from the lone pair to the vacant site, or where you can migrate. As you can see, it's actually fairly straightforward, just like our second pattern. It's important to recognize how the formal charges are affected by the electron movement in these two examples. My advice would be, every time you practice drawing your arrows and your resonance structures, calculate those formal charges. Make sure that you're practicing constantly until they become sort of second nature. Pattern number 4, a pi bond between two atoms of different electronegativity. So for instance, here we have carbon and oxygen. Oxygen is much more electronegative than carbon, and there is a pi bond right here in between, right? Usually when you have a double bond, you have one sigma and one pi. So that pi bond will migrate towards the more electronegative atom and contribute to that hybrid of resonance. The pi electrons will be more attracted to the more electronegative atom, causing the pi bond to be unequally shared. These two structures represent the extreme descriptions of the pi bonded electrons. The actual compound, as a reminder, is a hybrid of the two. So what we see in the lab, if we were to measure these bond lengths, these charges, is probably something in between these two structures as seen here. Pattern number 5, conjugated pi bonds in an enclosed ring. So this is where aromatics were coming to the conversation. Each atom in the ring has an unhybridized p orbital that can overlap with its neighbor. So when that happens, you'll have a scenario such as this one, highly conjugated, and just like we saw with conjugated systems, you can actually move those electrons. In this case, you have a closed system in the ring, so you can actually draw all of the arrows simultaneously, and that's perfectly okay. The pi bonds can be pushed over by one position, and it can be clockwise or counterclockwise, whichever makes you the happiest, because the result's going to be the same. This is a quick summary of all of the 5 main patterns as we saw throughout this presentation.